if you stand on the freezing snow-capped peaks of the Himalayas today,
Which is, an altitude of over 5 miles in the sky.
right, 5 miles up, if you're standing there gazing out, you might notice something completely baffling under your boots. You are actually stepping on ancient seashells.
Yeah. It sounds like a glitch in the Matrix, honestly.
It really does.
Finding marine fossils in a high-altitude, sub-zero desert,
Uh-huh.
it defies every basic intuition we have about how a mountain works.
But that is the magic of geodynamics. So, welcome to today's deep dive. If you're the kind of person who wants the aha moments without the, information overload, you're in exactly the right place.
Absolutely.
Today, we're exploring the incredibly dynamic, moving, and violently shifting physiographic layout of the Indian subcontinent. And we're drawing on the really exhaustive geological synthesis from The Making of India by K.S. Valdia.
It's a fantastic source. And, ancient literature actually described this massive, isolated landmass as Jabudweep, which contained Firafursh. But when you break down the actual landscape of this subcontinent today, the statistics paint a very different picture than most people expect.
Because we always think of the mountains, right?
Exactly. We associate the subcontinent with these towering peaks. But only about 11% of the geographic area is high mountains, meaning anything above 2,100 meters.
Wow, just 11%.
Yeah, just 11. And 18% is lower mountains and hills. 28% is made up of plateaus. But a massive 43% of the land is just plains.
Almost half the subcontinent is just flat ground.
Pretty much, yeah.
Which is crazy to think about. So our mission today is to take you on a geological journey to understand exactly how this vastly diverse layout was sculpted over billions of years.
And it really is billions.
Yeah. We're going to see how every single mountain, plain, and coast on the subcontinent is causally linked in one giant tectonic engine. Okay, let's unpack this. And I guess we should start with the absolute bedrock of the story.
Right. We have to begin with the peninsular shield. This is the foundation of the continent. It's this massive triangular landmass pointing southward into the Indian Ocean.
Okay.
And to understand the shield, you really have to understand cratons. The peninsular shield is made of 4 major ones. You've got the Darwar in the south, the Boster in the center,
Yes, sir. Okay.
the Sinkum in the east, and the Bundelkhand in the north.
Right, so a craton is essentially the ancient, rigid heart of a continent. Earth itself is roughly 4.5 billion years old. And these cratons date back anywhere from, 3.3 to 3.56 billion years.
Exactly. So they formed when the planet was still this chaotic, volcanic hellscape.
Right.
They're composite, highly crystallized blocks of crust. Because they cooled and hardened so early in Earth's history, they became incredibly dense, incredibly stable.
So while the rest of the planet's crust was, constantly melting and reforming and buckling over billions of years, these cratons basically just held their ground.
Yeah, they endured meteorite bombardments, extreme atmospheric shifts, whole planetary restructurings, all without being significantly deformed.
So they're like the unshakable foundation of an ancient fortress.
I like that analogy, yeah.
Like, the walls around them might crumble or get rebuilt over time, but that central keep has just survived all this planetary wear and tear for over 3 billion years.
But a fortress that old is going to have some scars.
Sure.
While the center of this shield is unyielding, the edges are heavily fractured. Take the western edge, for example, the Sahyadri Ranges, which most people know as the Western Ghats.
Right, the Western Ghats.
They stretch for 1,600 kilometers along the Arabian Sea, all the way from the Tapi Valley down to Kanyakumari.
But when you look at the profile of the Western Ghats, it doesn't look like a standard mountain range, right? Like with symmetrical slopes. The text describes it as a landing stair. It looks like a giant staggered staircase stepping down toward the ocean. How does a continent get stairs?
Right, so that step profile is the result of horse blocks.
Horse blocks.
Yeah, imagine taking a thick, solid block of hard clay and making deep vertical cuts into it. If you apply lateral tension, like pulling the clay apart slightly, some of those sliced blocks will slide downward just due to gravity,
Okay.
while others remain elevated. The elevated blocks are the horsts. So over millions of years, tectonic tension stretched and fractured the edge of this ancient shield.
So blocks just drop down.
Exactly, creating these sheer, steep walls facing the Arabian Sea with staggered flat-top terraces in between them.
So the Western Ghats aren't actually folded mountains pushed up from the ground like we normally think of mountains.
Oh, not at all.
They're just the fractured, cracked edge of that original 3.5 billion-year-old fortress where massive chunks of the wall simply fell away toward the sea.
Exactly. And if we connect this to the bigger picture, this incredibly rigid, stable block of crust with its fractured edges didn't just sit still. Driven by convection currents deep within the Earth's mantle, the entire peninsular shield broke off from an ancient supercontinent and went on a high-speed collision course, just barreling north toward the rest of Asia.
Which brings us back to those seashells in the sky. Because when an unstoppable 3 billion-year-old fortress slams into another massive continent, the resulting crash creates the 2,400-kilometer-long Himalayan arc, the roof of the world.
And the sheer scale of the Himalaya is just difficult to comprehend. It's not a single mountain range.
Right.
It is 4 massive, distinct tectonic terrains, essentially 4 parallel zones of crust stacked from south to north. And each one has its own violent origin story.
Okay, so let's walk through them. In the south, acting as the vanguard, you have the Siwalik Range.
Okay.
These are the youngest, lowest foothills, rising about 250 to 800 meters.
Yeah, and what's crucial about the Siwaliks is that they aren't made of hard, ancient bedrock.
Okay.
They're entirely composed of relatively recent river sediments.
Oh, wow.
Over the last 16 million years, rivers washing down from the rising mountains behind them just dumped immense amounts of mud, sand, and gravel.
Yeah.
So as India continued to push northward, all that loose debris got bulldozed and compressed into a new range of foothills.
So the mountains themselves are literally built out of the recycled trash of older mountains.
Pretty much.
That's wild. And tucked within these rugged Siwalik foothills are these flat, gravelly depressions called duns, right?
Right.
Which used to be lakes that got dammed up by tectonic uplift, slowly choked on gravel, and eventually dried out completely. They're like nature's forgotten bathtubs, holding thousands of years of track sediment.
Exactly. Now, climbing north from those dry bathtubs, you encountered the Lesser Himalaya, or the Himachal terrain.
Okay.
This sits between 600 and 2,000 meters high. It's a more mature landscape, known for gentle rolling peaks. But that gentle surface is totally deceiving because it's violently sliced open by incredibly deep river gorges.
Right, because the rivers here are cutting through the rock faster than the landscape can smooth itself out. And then, looming directly over the Lesser Himalaya, you hit the Himadri, the Great Himalaya. This is the domain of the giants, like Everest, Nanda Devi peaks, soaring well over 8,000 meters.
Yeah, and the Himadri is essentially a 10-kilometer thick slab of highly pressurized metamorphic rock. It's caught between 2 massive fault lines. You've got the main central thrust at its base and the Trans-Himadri Detachment Fault at its top.
Let's break down that thrust fault concept for a second, because it really explains the extreme height. You have 2 massive continental plates grinding against each other.
Right.
The bottom plate doesn't just stop, it forcefully wedges itself underneath, violently shoving the top plate miles up into the sky. It's like squeezing a tube of toothpaste from the bottom. The rock has nowhere to go but straight up.
That's a great way to visualize it.
Yeah.
This is a zone of intense, ongoing vertical uplift. I mean, the Himadri is rising right now as we speak.
That's amazing.
But once you cross over those towering peaks, the environment shifts drastically.
Yeah.
You enter the 4th zone, which is the Tethys Himalaya, a barren, high-altitude cold desert.
And here we are, back at the seashells. Because wait, how are there ocean sediments at the top of a frozen mountain desert?
Right, so before the Indian plate crashed into Asia, a massive ocean called the Tethys Sea separated them.
Okay.
As the peninsular shield barreled northward, acting like this continental bulldozer, it didn't just drain the sea. The immense pressure scraped the sediment right off the ocean floor.
The mud, the shells, everything.
Everything, the marine life, all of it. It scraped it up and compressed it. As the continental plates crumpled together, that ocean floor got hoisted upwards. So walking in the Tethys Himalaya today actually means walking on the crumpled, elevated remains of a vanished ocean.
It is the ultimate proof of plate tectonics. An ocean floor just turned into a freezing desert plateau. But while the mountains are rising, there's a counterforce at work.
Well, definitely.
There are rivers here, specifically the Sindhu and the Brahmaputra, categorized as antecedent rivers, meaning the rivers existed before the Himalaya ever started rising.
Right. You would think a mountain range growing directly in a river's path
Yeah.
would just dam the water or force it to change course.
Yeah, naturally.
But because these rivers were already massive, powerful systems, they had immense kinetic energy. As the tectonic plates began to slowly buckle and rise beneath them, the rivers simply carved their channels deeper.
So the river acts like a stationary buzzsaw. The tectonic plate pushes the mountain upward into the blade, and the river just keeps slicing.
Exactly.
The mountain does the moving, the river does the cutting. That's why you get these sheer, convex, slit canyons that drop vertically for thousands of feet.
Yeah, the uplift of the rock is perfectly offset by the downward cutting of the water.
But if you have stationary buzzsaws aggressively chewing through a rising mountain range, millions of tons of pulverized rock are being flushed downstream every single year.
Right.
All that rock has to go somewhere.
And it does. The sheer weight of the growing Himalayan mountains was so immense that it actually flexed the Indian plate downward. The crust sagged under the pressure, creating a giant trench, or what we call a four-deep, directly in front of the mountain range.
So the mountains grew so heavy they literally bent the earth beneath them, creating a massive moat at their feet.
Yes. And that moat rapidly became the dumping ground for those buzzsaws. The antecedent rivers washed unimaginable quantities of debris down into this trench. This filled-in depression is what we now call the Indo-Gangetic Plains, stretching for 3,200 kilometers.
Wow.
To grasp the volume of material we're talking about, consider the Namcha Barwa Massif. That one specific mountain mass is currently being eroded by the Brahmaputra River at a rate of 5 to 9 millimeters per year.
Okay, here's where it gets really interesting, because 5 to 9 millimeters sounds trivial. It's like the width of a pencil eraser.
Right.
But apply that across the entire surface area of a colossal mountain over millions of years. That is a catastrophic relocation of mass.
Absolutely.
The Himalayas are being systematically dismantled and dumped into the plains. And the plains, which make up 33% of the subcontinent, aren't just some random sandbox. The rivers actually sort the debris with mathematical precision.
It's all about water velocity and physics. When a steep, fast-moving mountain river suddenly hits the flat ground of the foredeep, it immediately loses its kinetic energy.
Because it hits the flat ground.
Right. It can no longer carry heavy loads. So right at the foot of the mountains, it abruptly drops all the heaviest, coarsest gravel and boulders. This creates the Babhar Plain.
Okay.
It's a highly porous apron of rocks. In fact, it's so porous that smaller streams actually sink and disappear completely beneath the gravel.
Right. Then as the water continues to crawl further out into the plains, it drops the medium weight material. This creates the Bangar, the older, slightly more elevated terraces of the plains. And the soil here is packed with kankar, which are these hard calcium carbonate nodules.
Yeah. And finally, the sluggish rivers carry only the finest, lightest particles, the silt and mud, far out into the flatlands, creating the Kedar.
The floodplains.
Exactly. These are the newer active floodplains that get a fresh layer of nutrient-rich mud every monsoon season.
So the landscape is literally a sorting machine based on kinetic energy.
It really is.
But this massive plain isn't purely confined to lush green river valleys.
Right.
In the west, this exact same continuous plain transitions into the arid Thar Desert in Rajasthan.
Yeah, and the Thar Desert traces the ancient dry channels of the legendary Saraswati River. It really highlights just how sensitive this vast, flat system is to subtle changes.
How so?
Well, a slight tectonic tilt or even just a shift in monsoonal patterns can starve a river system.
Yeah.
A thriving, muddy floodplain can transition into a sprawling desert just because the water supply shifted a few degrees away.
It shatters the illusion of the static map. A river vanishes, a desert blooms, and perhaps the wildest part is what lies beneath all this flat dirt.
What's fascinating here is that the basement rock beneath the Indo-Gangetic Plains is not flat at all.
Wait, really?
Yeah. If you could strip away the thousands of feet of river sediment, you'd see a highly uneven, jagged landscape filled with ancient hidden ridges, like the Lahore-Sargodha Ridge, and massive tectonic faults.
So it's exactly like a heavy snowfall covering a junkyard.
Yeah.
From the surface, you just see a smooth, pristine white field. But underneath, there are jagged edges, old cars, huge drops. The smooth surface is a lie covering a completely rugged, buried topography.
That's a perfect way to describe it. So we've tracked the rock from the mountain buzzsaws down into the sorted plains and burying the hidden ridges. But the rivers don't stop there. They are conveyor belts, and their final destination is the ocean.
Which brings us to the coastal margins. Sequentially going downstream here, the peninsular shield has two very different interactions with the sea.
Right. The west coast, facing the Arabian Sea, is primarily a coast of submergence. The land here is effectively dipping down into the water. And because of that downward tilt, you see sheer cliff faces, deep drowned river valleys, which are called estuaries, and almost no deltas. The rivers just plunge directly into the deep ocean.
But the east coast, facing the Bay of Bengal, is a coast of emergence. The land is gently lifting or building out, so you have wide beaches and massive deltas built by slower rivers like the Godavari and the Krishna.
Yeah.
You also get these huge lagoonal lakes like Pulakat, where the ocean is slowly being walled off by long, growing sand spits.
And the massive amount of sediment arriving on the east coast is staggering. The Ganga and Brahmaputra rivers deliver so much pulverized Himalayan rock into the Bay of Bengal that they've actually created a structure called the Bengal Fan.
The Bengal Fan.
Yes, it's the world's largest submarine fan. Basically a massive underwater avalanche of mud and sand that extends over 3,000 kilometers across the floor of the Indian Ocean.
3,000 kilometers, an underwater feature longer than most countries, built entirely out of dust, scraped off the roof of the world.
It's incredible.
And rising out of these oceans, you have the island chains, which are frankly just as geologically chaotic as the mainland. Take the Andaman Islands in the east and the Lakshadweep Islands in the west. Both are tropical paradises, but they are built completely differently.
Yeah, they are. In the east, the Andaman Islands are a classic island arc. The Indian tectonic plate is relentlessly grinding and underthrusting beneath the neighboring Myanmar microplate.
Okay.
As the Indian plate dies down, all the sediment and broken ocean floor sitting on top of it gets aggressively scraped off and squeezed up to the surface. So the Andaman Islands are essentially the ocean floor version of the Himalayas, just piles of crumpled oceanic rock shoved above the waves.
Meanwhile, Lakshadweep in the west is a completely different mechanism. It's built entirely of coral reefs.
But coral can't grow in the freezing, dark abyss of the deep ocean. It needs a shallow, sunlit foundation. And that foundation is the Chagos-Lakshadweep Bridge. Millions of years ago, a chain of massive volcanoes erupted from the ocean floor. Eventually, the volcanoes went dormant, and the heavy crust began to slowly sink back down into the ocean.
But the coral was already there.
Exactly. As the volcanic peak sank, the coral reefs growing around their rims just kept building upward, racing toward the light. So the Lakshadweep Islands you see today are actually towers of coral sitting on top of drowned, ancient volcanoes.
This raises an important question, though, because if these islands are built on sinking volcanoes and scraped ocean floors, they must be incredibly sensitive to ongoing tectonic shifts, right?
Oh, they're actively reshaping as we speak. Sea level changes and continuous tectonic pulses are rewriting the coastlines right now. We can actually map submerged, drowned terraces off the coast of Lakshadweep that show exactly how the islands have sunk in distinct, sudden drops over geological time.
Wow. So let's sort of synthesize this whole journey for you guys. We started with the indestructible 3.5 billion-year-old cratons, the ancient fortress foundation of the peninsular shield.
Right.
We saw how its collision with Asia resulted in the violent toothpaste tube uplift of the Himalayas. We watched antecedent rivers act as stationary buzzsaws cutting through the rising rock.
Yeah.
We traced that pulverized mountain down into a massive sagging four deep, sorting itself by kinetic energy to form the flat plains that hide a jagged, buried junkyard of rock. And finally, we watched that sediment spill out into the oceans, creating massive 3,000-kilometer submarine fans and surrounding islands born from scraping plates and sunken volcanoes. So, what does this all mean?
Well, it means the map of India isn't just a static piece of paper. It's a freeze frame of a violently active geological engine running at full speed. It's a perfectly connected, closed-loop system where the destruction of one feature is the exact mechanism that builds the next.
The mountains literally supply the material to build the plains, and the plains act as a conveyor belt feeding the coastal shelves.
Which leads to a fascinating, entirely new variable in this ancient system. For billions of years, this tectonic engine has relied on those rivers, relentlessly carving the mountains and delivering millions of tons of sediment downstream. That sediment holds back the ocean and builds the coasts.
Right, the unbroken conveyor belt of rock.
But over the last century, humans have fundamentally altered that equation. We're damming those antecedent rivers. We're trapping that heavy sediment in reservoirs high up in the mountains.
Oh, wow.
Yeah. If we artificially shut off the supply of rock dust that feeds the plains and builds the deltas, what happens to the coastlines?
They don't get replenished.
Exactly. As sea levels rise and the coasts are starved of the fresh sediment they need to keep emerging, we might actually be engineering the rapid sinking of our own margins. We are actively interrupting a billion-year-old geological machine.
We are starving the very coastlines that rely on the destruction of the Himalayas to survive. That is a chilling perspective on human engineering. Well, thank you for joining us on this deep dive. The next time you look at a map or step onto a flat plain, we hope you don't just see permanent dirt. We hope you feel the slow motion ocean of tectonic movement remaking the world right beneath your feet. Catch you next time.
वीडियोस बनाने हैं फिल्मोरा है ना।